So I had a colleague come by and want to chit chat. Sorry, I'm back now. So if we have got in that fifth subinterval, let's see what that looks like. So inside of the fifth subinterval, we see that we go from 4 to 5. So if we look at the left-hand endpoint on that subinterval, then we need to know what the y value is. So notice it actually goes down in this case. So this would be the y value, -1. So f at 4 in this case is actually a negative value, -1 times delta x. So we're actually going to have a -1 area inside the rectangle inside of the fifth subinterval. Inside of the sixth subinterval right here, the left-hand endpoint is 5. And so again, we're going to have a negative signed area. Specifically, we're going to take f of 5 times delta x. F of 5 times delta x is 1. F of 5, in this case, f of 5 turns out to be, well, if we look on the picture, it is -1, -2, about right here, -2.5. Excuse me, so I'd say it's -2.5. So that means the signed area is going to be -2.5. So you just add those things up, right? So 3.5, 2.3, 2.5. So in the online key, just to be kind of with that, instead of 2.3, they say 2. It's whatever, horseshoes and hand grenades, because you're just kind of looking at it. So that's going to end up giving, for our left-hand Riemann sum approximation with 6 subintervals, otherwise known as L sub 6, that's going to give us 8. Right? So specifically what we had was we had a positive area of 11.5 minus 3.5. This area over here that was below was -3.5, and that's how we got 8. So L sub 6 in this case we found to be 8 for our approximation to the area under the curve. If we do the midpoint, it's going to be very similar, right? We're going to take this exact process that we had before. Inside of each subinterval, we are going to sample. So we take all of this and we're going to use the exact same process. I copy. I come down here and I hit paste. Actually, let me do a new page after. And I'm going to paste. So this is what we're going to look like, but in this case, we're going to sample at the midpoints, and we're going to use 6 subintervals, right? So let me get my picture again. This one, and cut, bring it down here, and paste. So now if I want to do the midpoints of each subinterval, I still have delta x equal to b minus a over n, which is 6 minus 0 over 6, which is 1. So each step is still 1. Here's 1, 2, 3, 4, 5, 6 steps. It's just this time that star represents the middle point of the interval. So we take some x value in the first interval. And in this case, that some point that we pick is going to be the midpoint. So in the first interval, we're going to take f of, well, the first interval goes from 0 to 1, so the midpoint would be 0.5, also known as 1/2, times the delta x of 1, plus f at x sub 2. Well, what is the midpoint of this interval? It's going to be 1.5, otherwise known as 3/2, times 1 is my delta x. Then inside of that third interval, third interval, it's going to be 2.5, otherwise known as 5/2. Delta x is 1, plus, and notice we just go up by 1 every time. So this is going to be f of 7/2 times 1, And this is going to be f of 9/2 times 1. And this is going to be f of 11/2 times 1. So notice we just end up having 1 times all these things. Well, f at 1/2 is 3. F at 3/2 turns out to be 3.8. 3.8. F at 5/2 ends up being 3.5. And just to make sure we're clear where that came from, so where did 3 come from? Well, if you look inside of the first interval and you look at the midpoint of 1/2 and go up, its height is 3. That's where this 3 came from. Inside the second interval, which is here, if you look at its midpoint and go up, it looks like that point right there has a height of about 3.8. And that's where this 3.8 came from. Then, if we look at 2.5, which is right here, and we go up like that, it looks like we get out, that's where we get out our 3.5, which is the 3.5 we have right here. So if we continue this process, we're going to get 0.25 times 1, and then we're going to get a -2, because notice that now we come inside, so we should have got a 0.25 and -2. So now we see that that's inside of this interval. I look at the midpoint and I go down, and it looks like I get a -2, and that's where this -2 comes from. Times 1 plus, what, -2.9 times 1. So it looks like, so plus -2 plus -2.9. It turns out that if we have a midpoint Riemann sum approximation with 6 subintervals, we calculated that we got 5.65 square units for this area. So what do we get? Let's look. What does that mean? So let's go back here. Up here, notice we got 8 when we took the left-hand endpoint, but 5.56 when we took the midpoint. And remember, so this midpoint would have given us this rectangle, and this midpoint would have given us this rectangle, and then this midpoint would have given you this one. So it just does, in this case, midpoint's like real low here, our midpoint is here. It just is, for this function, it does a better job of hugging the function. It does a better job. All right. So this Riemann sum is the approximate area. Right? So let's see. Let's now go on to 2a. So for 2a, we are evaluating this Riemann sum for this function from 0 to 2 with 4 subintervals taking the right endpoints. Explain with the aid of a diagram what this Riemann sum represents. So with the diagram, they mean they want us to draw a graph. The first thing you know, if you factor out an x, is that this is x minus 1, so it has zeros at 0 and positive 1. Also, because the leading coefficient is positive and this power is even, we know that it opens up, up. And since the power of each, the multiplicity of each 0 is odd, we know it crosses through each 0. So if we pull that out, it crosses through each 0, and here's how it crosses through each 0. So first, crosses through this way, and then this one crosses up this way. So it looks something like that, right? So we're going to be going from 0 to 2. So here is the area from 0. That's 1, we said. So then this would be 2. If I draw it a little bit better. So this is 0, this is 1, this is 2. Not quite drawn to exact scale, but we're going to have to find out what that area turns out to be, where we've got a negative signed area because it's under the graph and a positive signed area. So let's see what we have. So we're using 4 subintervals. So when we're thinking b minus a over n, this is 2 minus 0 over 4, because we have 4 subintervals, n equals 4. And so each step is of size 1/2. So I'm going to take 1 step to 1/2. So here's my first step, and here's my second step, here's my third step, here's my fourth step. So we're going to have 1, 2, 3, 4 subintervals. Makes sense. Yes. And so if we're using a right-hand Riemann sum, so we're doing a right-hand Riemann sum. So a right-hand Riemann sum with 4 subintervals, then that means I'm going to have, we're doing the right-hand endpoint, for the first interval, it's going to be f at 1/2 for the first interval times delta x plus f at, on the second interval, the right-hand endpoint is 1, f at 1 delta x plus f at, well, in the third, the right-hand endpoint is 1.5, also known as 3/2. And then the last one, the right-hand endpoint for the last subinterval is just 2. So the last one is going to be f of 2. Let me move it out of the way to get more room. So it's just going to be f at 2 delta x. So f at 1/2, well, if you come over here, f at 1/2 is just 1/2 squared minus 1/2. And that's going to be 1/4 minus 1/2, which is negative 1/4. So this is negative 1/4 times a step size of 1/2. So that's going to be negative 1/8. F at 1 is just going to be 1 squared minus 1, which is 0. It's going to be 0 times, which is going to be 0 times a height of 1/2. So we're going to get nothing out of that rectangle. So the first rectangle goes down to a height of negative 1/2, and so it looks something like that. The next one is a height of 0, so it's real small. It's non-existent. And then for the next one, f of 3/2, we're going to take 3/2 and square it minus 3/2. So that's 9/4 minus 3/2. That's the same as 9/4 minus 6/4, so we get 3/4. So this is 3/4 times 1/2, which is 6/8, right? Plus the last one, when you plug in 2, you get f of 2, that's 2 squared minus 2, or 2, so this is 2 times 1/2, which is 1. So what we're going to end up getting is what? But 1 is the same as 8/8. So we're going to get, oh, they got 13/8. I got 13/8. So let's see what silly thing we did. We should have gotten 3/4, 5/2 times this, 0, 3/2, and 2. I was right on everything. So you're saying, I think she got something. Say that's 1/2 and 2. 5/2 times 1/2. 5/2 times 1/2. So I'm right with this. That's 0. Oh, that should be 3/8. Sorry, I got excited right here. This should have been 3/8. So that's going to end up giving you 8, 9, 10, 11. 11, 10. So that's going to be 10/8, also known as 5/4. Right? Cool. So It's easy to get lost in the sauce, so you really want to make sure that you are doing a good job of organizing your work on this. So it's really clear where you're evaluating the function over here, where you've got your step size, and where you've got your Riemann sum, because it's easy to get lost in the sauce. So that's 2A. So now let's look at something like number 4. So number 4, it says this is a definite integral. So we know that the integral from a to b of f of x dx is exactly equal to, well, it's the sum at the f sub xi's delta x, where I equals 1 to n, and the limit as n goes to infinity, right? So that is what an integral looks like. So this is the sum of a height times a width, so that's just a rectangle. And I let I, the counting index, this thing right here, I let it run from 1 to n to make n rectangles. And then this lets there be infinitely many, and that's when we get the exact area. So I need to look at something like this and turn it into something like this. We are changing the form. So in number 4, if you have the limit as n goes to infinity, we know that that's automatically going to be an integral. And if that limit is sine of x sub I delta x, then that means we're integrating sine x dx, right? And we're taking the limit of a sum. We're summing up these I equals 1 to n, these n rectangles. So each one of these is a rectangle. We've got n of them. Then we let the number of rectangles go to infinity, and that's when we get exactly the area. And they told us, guess what? It's the area on this interval, so that means it's from 0 to pi. So this would be a way to describe that infinite sum. So what that's telling you is, I could take all this, I can take all that, and move it over here, so that if you asked me to evaluate that infinite sum, all I would tell you is, look, that's exactly equal to this. If you want to evaluate it, is just this integral. That integral I can find using the fundamental theorem of calculus. Fundamental theorem of calculus. And what it tells me is to take the antiderivative sign, and that's negative cosine, because the derivative cosine is negative sine, so I need a negative. And we're going to evaluate that at 0 and pi. So I'm going to take negative cosine, I'm going to plug in pi, then I'm going to subtract negative cosine, I'm going to plug in 0. So cosine of pi is the x-coordinate over there is -1, hit it with a negative, it's going to be 1. Cosine of 0 is 1, make it negative again is +1, and so you're going to get 2. So this infinite sum is exactly equal to 2. Pretty amazing. Now if I take this and I copy it, copy it, then I can make another page. So here if I hit paste, I've got number 5. It says if the area from 0 to 6 is 10. So I have some function f, I don't know what it looks like. Take the area from 0 to 6, in that area, oh, here's the way I can show you that. Let's say I do it like this. So take the area from 0 to 6, and that area is 10. And then I take the area from 0 to 4. So 0 to 4, and that pink shaded area, 0 to 4, that pink shaded area is just 7. So first I did all the yellow area from 0 to 6, and that was 10. But then the smaller shaded area in here was just from 0 to 4, and it was 7. Well, then I think it's pretty clear. You know that the integral from 0 to 4 of f of x dx plus the integral from 4 to 6 of f of x dx is just going to equal the total area from 0 to 6. But we know that the area from 0 to 6, you told me, was 10. The area from 0 to 4 was 7. And so now I'm ready just to solve, and I get that the area from 4 to 6 under the f curve is 3. Okay. So we really do need to see this first thing written out to get full credit. I need to understand that you see one area plus another area equals another. You cannot just write down the answer of 3. Okay. So that's number 5. Then we get to number 7. So when you're thinking about number 7, we're trying to figure out which of these is f, which one is f prime, and which one is the integral from 0 to x of f of x dx. Okay? One way to think about that is this is just big F of x, right? This is just the antiderivative, right? This is just, actually it's f at x minus f at 0 is really what it is, right? But the way to think about it is, if I were to take this derivative, so if you take this derivative, you're going to get f, and if you take this derivative, you're going to get that. So you could think of this as your first function, you take its derivative to get f, then you take its derivative to get f prime. So that means if I'm thinking about the original function, that means you can think of this with the dummy variable t dt as our function, and this as our first derivative, and f prime is actually the second derivative if our original function was the integral. So I think that means if you think about it long enough, you're thinking about some things like, look, do you see right here where this one has a peak, this one gets a 0? So that also where this one has a valley, this one has a 0. Where this one has a valley, this one has a 0. So I think it's pretty clear that B is equal to the derivative of C. So I take the derivative of C to get B. So C, you take a derivative to get B. So that means it's either f or it's f prime. Let's see if we see any other relations. Oh, there's the other relation. But look here. If you take the derivative of A, you get a 0. So at this peak it has a 0, and then at this peak it has a 0. So I think that the derivative of A is C. So I think that A, if you take its derivative, is C. So this is A prime. So if you take a derivative of A, you get C. If you take a derivative of C, you get B. So a derivative of C is B. So I think A would be the integral. B, so that means A would be the original. And then when you take its derivative, you get, let's see, when you take its derivative, you get C. Which is the function. Then when you take C's derivative, you get B. Right? What do you think? Not easy, but notice the easiest way to think about it was just find out where one has a peak or a valley, something else has to have a zero. You can do a more complex and detailed analysis, thinking about increasing, decreasing, and concavity, if that floats your boat. So then we look at 11, 13, and 15. These are just, instead of using the first fundamental theorem of calculus, remember, the first fundamental theorem of calculus says that if f is continuous on AB, then the derivative of the integral is just that original function. The second fundamental theorem of calculus says if f is continuous on AB, then the integral from a to b of f of x dx can just be evaluated by hand by taking the antiderivative at b minus the antiderivative at a. Okay. So unfortunately, I have to leave to go cover for period class for somebody else. So I will finish this video in a minute.